Hello everybody, this is Mr. Longo, and in this video we are going to cover throw and drop quadratic application problems. Now the reason these are kind of in a little league of their own is because there are two models. One model represents the height of a falling object if you just drop it, and another one is if you throw it. Now here's the thing about dropping. We can use the throwing formula because, well, if we just drop it, it has an initial velocity of 0. Okay, so we'll just keep that in mind. So in both of these equations, h represents the final height. And you'll notice in both equations we have an h sub 0. That is your initial height, because that means the height at 0 seconds from when we start. T in both of the equations is obviously time. And VO is your initial velocity. Now, the initial velocity is tricky. So if you throw something, an object, up into the air, so if we're throwing up an object, that would be a positive initial velocity. If we are just dropping it or actually throwing it horizontally, so if we were to just throw something out parallel to the ground, our initial velocity is actually 0 because the negative 16 is force of gravity and our velocity is in terms of going up and down because we're finding a height. So if we just throw something straight out in front of us, the initial velocity is the same as dropping it in terms of up and down. Our last situation is if our initial velocity has been throwing an object down towards the ground. Well, then we would have a negative initial velocity because we're throwing it down, okay? So again, if we're throwing an object up in the air, it's a positive initial velocity. If we're throwing an object parallel to the ground horizontally, or if we just drop it, we have 0 initial velocity. And if we're throwing it downward, we have a negative initial velocity because we're getting, closer to the ground already. So what we're going to do is use those formulas to answer a couple of questions. So a rock is dropped off of a 1,450 foot tall building. How long would it take for the rock to hit the ground? So again, we have to remember what the different parts of our equation represent. So it says that the initial height is 1450, but when we hit the ground, that's a final height of 0. So our final height is 0. That's equal to, now we have our drop formula, which means we have no initial velocity. So that would be negative 16t squared. Since we have no initial velocity, we don't have the need for that, plus our initial height of 1450. To solve this, that's simple. We're just going to use square roots. So we're going to subtract 1450 from both sides. And then we're going to divide both sides by a negative 16. And that would give us a 90.625 is equal to t squared. Now that means our time is squared, so to get rid of that we have to square root both sides. So if we were to just square root both sides, we would end up with t is equal to 9.52 seconds. So that means if we were to drop a rock off of a building that tall, it's going to take 9.52 seconds to hit the ground. Now, of course, that's in a perfect world where we're ignoring wind and friction, because, obviously, if this was a real life problem, we would have those things to take into consideration as well. So now we're going to take another equation, s is equal to 32t, which means the speed of an object is gaining 32 feet per second for each second that it travels. So if we were to take that into account and say how fast would the rock be traveling when it hit the ground, that's just s is equal to 32 times the amount of time it's been traveling, which is 9.52 seconds. and that would give us a speed of 304.64 feet per second. Okay, so that's our speed as it's hitting the ground, which, my goodness, I would not want to be hit by that rock. Now again, at that time, maybe it reached its terminal velocity. Again, this is just kind of an example of a word problem. We are not considering, you know, wind and wind speeds and all that kind of stuff. All right. Now, this example over here is going to give you a velocity. So that's why this one's going to require some more algebra. You'll most likely use the quadratic formula, because a water fountain shoots a stream of water up from a spout that is 10 feet above the ground and at an initial velocity of 30 feet per second. Notice it said it's shooting up. So our initial velocity is going to be a positive 30 feet per second. And the water is going to land in a basin that's 6 feet above the ground. So how long does it take for the water to go from the spout to the basin? And you might have seen these walking through like some sort of botanical garden or some sort of fancy building where they have those little streams of water that shoot from one end and land in another end. So what we're going to do is we're going to go calculate how long that takes to happen. So our initial height and our final height, we have to make sure we read carefully. So it lands in a basin that is 6 feet off the ground. So our final height is 6. That's equal to our negative 16 t squared plus our initial velocity. Our initial velocity is going up at 30 feet per second. So we have plus 30t plus our initial height. Now this said our initial height was 10 feet off the ground. So is plus 10. And now we have to solve this. So since we're working with a quadratic, it would be easier if you were to subtract 6 over to the other side, and that would give us a negative 16 t squared plus 30t plus 4. Okay, and of course that's equal to 0 now, but we have a quadratic in graphing form. So if you want to save yourself a little bit of, time with some big numbers, since we can factor out a negative 2 here, it would be easier to work with 8t squared minus 15t minus 2. Again, that's optional because we have a graphing calculator. We can just plug all of these big numbers in and your graphing calculator will handle it fine. But really, it's up to you. So since we have such a really big equation to work with, you could always try to factor it. It might not necessarily factor. So I'm just going to show you how to use the quadratic formula again. So our quadratic formula is going to be opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And then you just need to work that out a little bit. So obviously we're still going to have our 15 plus or minus. If we take care of the inside, negative 15 squared, and then minus 4 times 8 times a negative 2 is going to give you 289. And that's all over 2 times 8, which is 16. Now you should know that the square root of 289 is 17. If you did not know that, well, you know it now. So 15 plus or minus 17 all over 16. Okay, so that would split. So 15 plus 17 is 32 over 16. And 15 minus 17 is a negative 2 over 16. So we have two answers. Our time for all of this to happen is 2 seconds or a negative 1/6 second. Now, we know for a fact that we can't go back in time. I mean, that would be really cool if we could, but we can't. So we don't even consider that as an answer. So the time it takes to happen is 2 seconds. Okay? Because we can't go back in time. All right? Well, that's it for this video. This is Mr. Longo, and I'm out. See you, bye.